All right, thank you for having me here. It's a pleasure. I'll be talking today about some spectroscopy that we're doing with Webb. I'll be talking about the garden survey on behalf of the garden team. And, oh gosh, her photo went away, but I do want to highlight the work of Camilla Pacifici, whose photo was on this slide a second ago. And she's really the two of us are really running this, and we're at Space Telescope. The near-spec microshutter array is used. The microshutter array is one of the modes on it, and it consists basically of a little grid, kind of like a screen grid in your window, and you can open and close shutters on this grid in order to create spectral slits over galaxies. Here's a picture of a deep field with galaxies in it. We're zooming into that little box over here, and then zooming into that box here. And you see these little slitlets that you can open on galaxies. You can get spectra through these apertures, and you can configure it as you wish. Garden is a cycle 1 program that uses this. It's GEO 2123. It was observed kind of late, it's almost in cycle 2 in September 2023. It consists of 56 galaxies of redshifts 1 to 6 in the UDF, 1 MSA pointing. We use the high resolution grading, 75 hours, probably about 57-ish on source, no proprietary time, data to be released in the spring. We went very deep on purpose. Here is Garden in red. The 4 MSA quadrants are pretty distinctive. Right, we're kind of below the UDF-ish a bit to get one of our favorite galaxies that you'll see. And then the J's image is below, and it overlaps a lot of other very important surveys, including SMILES and a bunch of other MIRI stuff. It's really good. Okay, UDF is a good place. So here we are. This is the stellar mass mean sequence in increasing redshift bins. This is old candles data, but it's just to show you that if we go with your star formation rate versus stellar mass, a kind of typical galaxies are in gray, but as in the candles, our galaxies are in red. And as you go to higher and higher redshifts, we're tracing the galaxy population to first order. We did go for brighter galaxies. We did go for, more highly star-forming larger galaxies because, as you'll see, we'll be testing a technique. And we wanted to get continuum. Okay, getting continuum with Webb, as you know, is hard. So this is just a couple of numbers just to remind you, it's first billion years, but, kicking it out a little further, you can go down in redshift, and really Webb is just opening this redshift range like you wouldn't believe. Before that were just some smudges that everyone said, oh wow, look at these rotating disks. You actually see, it's a zoo out there, and it's quite interesting, and we're getting these beautiful spatially resolved images. This is back to HST candles, but it's just showing you our technique. We called it slitless stepping, as you saw in Erica's talk. Thank you. This is kind of the old Dutch drift scanning. We're scanning the slit across the galaxies. I called it slitless stepping at the Institute. It was an internal word for an old IFU dither pattern, and that kind of stuck. And so it's kind of gotten out there. That's why it has that weird name. I'm sorry. And so we step across the galaxies. There's also another slitless stepping program that does it quite differently. It takes the whole MSA and shifts it around. And that they have a paper out on that I encourage you to read. So here's a cartoon of our technique. This is an MSA quadrant, not to scale. It's you fit a lot more galaxies on it than this. And we step across actually 6 times. This is an old figure. But you can see big galaxies get many steps. Small galaxies get fewer steps. Small galaxies tend to be fainter. And so we sit on those fewer steps a little longer. And then it goes down to the limit where you have one galaxy that's so small, it fits in one shutter and it gets all the exposure time. You can just let your mind wander and you can find a bunch of creative ways you can do this. This also really helps a lot because there's a bunch of broken shutters. And you can kind of dance around that. We shift, reconfigure, shift, reconfigure. Okay, and so we were able to fit 56 galaxies on with the high resolution. With lower resolution, you can fit hundreds to thousands. Here's the IFU. It's 3 by 3 arc seconds versus 3.5 by 3.5 arc minutes. The multiplex is really fantastic. Please dither your data on NearSpec. Please talk to me if you have any questions on how to do that. The nod is, in my mind, for point sources. So we do a 5-point dither pattern. This is typical, you know, observing from the ground, I guess, you know, so we don't do that so often. So we do here, we do step back, and then front, and then front. It's a bit of a dance, and we move through it. So you're doing it, but you can see, you can choose the size of your dither pattern based on what you want out, you know, based on what kind of data you want, how the depth you want. And dithering gets you past a lot of the bad pixels. It gets you much higher quality data. Okay. I'm not going to spend too much time on this, but cube building for this is not complex, as Jane would say. Jane is the lead on this. It just really uses the WCS of the MSA slitlets and the JWST data models to just take the spectra and stick them back onto the sky and then put them into a cube. Jane wrote this rather fast and was able to just test it on data, and it works beautifully. We're actually finding some issues that we're fixing with the data. So it's helping us make even better data cubes for the IFU. So we're also working hard to find and improve detector effects. Because we're going so deep, you know, we wanted that continuum. When you start, please look at your rate files, your rate in files, you start seeing a lot of stuff. And you'll see as you get further improvements in the pipeline, anything we fix, we put in the pipeline, we test it. You'll see improved 1/F corrections. This is work by Mike Reagan and Eddie Bergeron at STScI, both co-Is on this program. Improved snowball detection, that's already in there. Time variable detector bias, even odd row amplifier patterns. Is there scratching? I don't know if there's a bug somewhere. Even odd amplifier patterns, improved DQ mask flagging for high random telegraph noise pixels, improved thermally corrected ducts. Look at your data. Also, shutters are intermittent. Sometimes they operate, sometimes they don't. Please, you can see in your spectra, you can see that when you start reducing the data. So please, if you have data now, reduce it with future pipeline versions, and you'll see an improvement. There's some ugly things in there. Have a look. Garden data is going to enable maps of galaxy outflows, galaxy winds, gas, and sometimes stellar kinematics, metallicity, dust attenuation, BPT, and more. I'm going to walk you through, slow down, have a little more fun now, and walk you through 2 example galaxies at, God forbid, redshift of 2. This is the coffee pot galaxy at redshift 2 from the ground. We thought it was a rotating disk. It is not. It's a hot mess. These images are stunning from NearCam. Stellar mass of 10 to the 10.7, star formation rate 10 to the 2.4. Call it the coffee pot because it has an arm and a spout and a top. And it's easy to do that, to talk about different features when you name it. Here it is in the UVJ diagram on the left. It is kind of on the dustier side of the blue star forming galaxies. This is an integrated sense. It was chosen to be high mass, high star formation rate, no shocker. And it is, again, larger, you know, in its and at higher mass. It was chosen to be big and star forming, but it's not entirely off all of these relations. Here is just, you know, eye candy. F90, so rest.3, about B band. F444, rest 1.5, like JH band. You see the same story that people have been talking about. I think Ari and you, or a lot of people talked about this. You see how, you know, we see this local too. You know, you see highly dust and shrouded things, especially in the centers at higher redshift here. And then you see in the IR, you see the old stars come right through. Dust and shrouded center, as you will see. It's dust in the coffee pot. We did SCD fitting. This is very preliminary. Sorry, the map doesn't go out that far, but you can see, A sub V goes up to 3, way down in there. So this dust and shrouded center with this beautiful ALMA detection right down the barrel there, right on the dust. And so it's one of the compact star forming galaxies in the Gomez Guijarro Elbaz paper. And so it's really beautiful to be able to get these maps. And that was just from the broadband photometry. We didn't even incorporate the spectra yet. We're in the middle of that. Now we just looked at sodium deabsorption. We have sodium deabsorption, guys, at redshift 2. Can you believe this? This is shocking, you know. It's incredible. We were aiming for this at Redshift 2, so what we wanted, and then we got it at this resolution. Thank you, Webb. It's a $10 billion difference. And you can see it is amazing. It doesn't go on where it's crazy dusty. It kind of goes around that. Sodium D does need dust shield in order to exist. So it's not surprised it's in dusty region, but it's not in the very dusty region. Thank you. I'm going to flip through this a bit more. And so that's very interesting. Here's a bear claw galaxy at Redshift 2. Similar mass and star formation rate. That's why we call it the bear claw. Look at this. It looks like a merger here, but then it has this bar and the spiral arms here in the IR. Same thing. Bright, star forming on the dusty side. This is the fun part. Look at this map. You even have channel maps of this. You can scroll through it. It's incredible. I feel like a radio astronomer. You can look at this beautiful rotation curve, rotation map. Look at those numbers. Now we're going to make a velocity map, a velocity curve of this. Rotation velocity versus radius. It goes rather fast. 240 on one side max, 315 on the other. This is not inclination corrected. This is raw. Let's measure an inclination. This is hard to do locally. Inclination 30. Measured it at R25 from the 444 image, trying to follow the stars. 15, plus or minus 15 degrees. We don't know. It's hard to measure that well. So here it is, velocity versus radius with those inclination corrections with the error. Of course, there's a large error because we don't know the inclination well, but it goes up to 600 and 500 kilometers per second. 8 kiloparsecs. This is wild. Here's what the stars are doing. Not much. Inner part looks maybe a little bit of maximal disk-ish, and then it just falls off. So, there's more in there. This is just the tip of the iceberg. These are just some fun targets that we're writing up. And we're hoping to reduce data cubes and give them out to you guys so you can have fun with this too. And then briefly, we're going to do it again in the Meadow survey, not as deep, but for hundreds of galaxies. And here's the picture of Dr. Camilla Pacifici, who's co-PIing this with me. It's a cycle 2 program, was just observed this spring, 300 galaxies with photos. These run redshifts 2 to 4, 6 MSA pointings, 67 hours. And we're going to get, galaxies in trace kinematics, cosmic web, spin alignment, all that jazz. So I'm just going to leave you with that, and then finish on time. Thank you.
Thanks, Susan. That was perfectly on time. Questions?
So what do you make, you showed a stellar velocity profile there. That's a stellar rotation curve, basically, or a stellar velocity profile?
No, I'm sorry, Mike, that's an old school decomposition. We have stars, but we haven't, I haven't shown you the stellar kinematics. So that's not a measurement
of stellar velocities from this data?
I haven't showed you this. We have stellar kinematics, but I haven't put enough time to put it in the talk.
So that's what you would get from the stellar
if it's stars alone, yeah.
Profile.
This is an old school rotation curve decomposition.
Got it.
And then the difference would be gas and dark matter. Yeah. We're going to apply for ALMA for this thing. Please give it to us.
I'll do that.
We could do, of course, invert Kennicott-Schmidt, but that's ugly.
Hey, Susan, Arjen here. The sodium deabsorption, that's really cool. Did you see blue shifts compared to systemic red shifts?
You mean the line being blue shifted? I don't want to say anything yet. I don't want to say anything yet. It's still very preliminary, and you can see where, yeah. I'll show you later. I think there's winds. Perhaps. I think so. In some of this.
Susan, the rotation curve looks super slowly rising. Is it like a giant core?
Let's have a look. Yeah, it's just taking its time there. Whoa, look at the numbers though.
Yeah.
We're used to looking at 200 there, right?
It's going from 100 to 500 over 8 kilo.
I thought you meant the inner rise.
No. It's very, very slow. Very slow.
It's taking its time. This is weird. Yeah, I never seen anything like this, dude.
I mean, yeah, maybe.
No, well, actually, when you look at the map, when we look at the channel maps, we were just down in Santa Cruz doing this. When you look at the channel maps, this side you see a beautiful spider diagram. This side you see more solid body, straight line. It's really weird. But you see like textbook spider diagram on one side, and the other you see more solid body. But I don't think it's solid body. But it would be on the red side that we're seeing more solid body. It can't be one solid body on one side and spider on the other. It's a weird object.
So Susan, okay, so just
Yes.
roughly, it seems like the dynamical mass you would infer, if it's 630 at like 8 kilograms, so that's like something more than 10 to the 11 solar masses in terms of the dynamical mass. I forgot if you said like what
The
you.
dynamical mass with the, sorry, my computer's not happy, but the dynamical mass is, you mean from this?
From this, with 630 at 8 kiloparsecs.
Yeah, that's going to be much higher, but I mean, I haven't done the math, but yeah.
Okay, so, but I mean, I forgot if you said like if you have a stellar mass, like I was just wondering how the dynamical mass compares. Oh.
Here it is, here it is.
Oh,
So
sorry.
we have better than that. We have taken the stellar mass we create a stellar mass map from SCD fitting. I skipped over a lot. And then in that map, we binned it in different annuli. And so we now have a radial profile of the stellar mass. Then we did the math to just infer, to measure the rotation only due to those stars. So this is the difference you look at because it's spatially resolved. Yeah.
Thanks.
Thank you, Arian.
So I was wondering if the data from Garden and/or Mattles could allow us to look at higher moments of the line of sight velocity dispersion of each spexel, because if you can do that, then we can easily fit, say, Gaussian intermittent polynomials to the velocity map and see whether they, like, when people are debating whether this is a solid body or rotation curve, then just by looking at the higher moments of the velocity dispersion, velocity distribution, you can see whether that's really rotating or solid body rotation, right?
We're not there yet. I don't know if the data can handle it.
Okay.
I will only do it if it's worth it.
Cool.
But I appreciate it.
Thanks.
Okay, last question from Seiji.
Yeah, thank you. Yeah, I'm very interested in this method. Yeah, I always wondering if MSA stepping method or IF cube, which is more efficient, and yeah, this is really beautiful. My question is that, yeah, you are choosing the Diesel method, 5 Diesel pointing, so the sensitivity should be heterogeneous. So this heterogeneous cube, sensitivity cube, might bring any systematic bias in your measurement, or?
So the dither pattern here is only for, I only showed it for one shutter.
Yeah, okay.
Imagine you have this. The dither pattern is also meant to get rid of these, you know, the grid pattern, the holes between the, you know, there's a space between the shutters this way and that way. And so you dither over it.
Okay, so
Yeah.
regions
So
should
on
be
the
covered.
edges, there'll be, you know,
yeah, okay.
some that are not getting the full exposure time, but you know that. And so you make your slits long enough.
Okay,
Even I make my slits long so I get sky, I get local sky. Yeah.
thank you.
Thank you.
Awesome, let's thank Susan again.